Hello guys, welcome back to my channel. My name is Joseph. So today what we are going to do is that we are going to take a deeper look at a simple one-dimensional population balance. By one-dimensional, we mean that we are going to take a look at a population balance equation that is one-dimensional in terms of the internal coordinate. Or for example, if you say that you are modeling a crystallization system, then it could be the size of your crystal, right? So we are going to look at a population balance equation that is one-dimensional, not in the physical space, but in the internal coordinate space. So let's jump straight into it. So let us just first do a quick recap on the general population balance equation for a continuous and deterministic system. So what we meant by continuous and deterministic system is that if you are dealing with a particulate process, for example, then the number of particles in your system throughout time and throughout the internal and external coordinate space, or the physical space and the internal coordinate space, such as your particle size, the space that represents your particle size, for example, must be abundant enough so that the entire behavior of the system can be assumed to behave as a continuum. So that is first and foremost the population balance equation that we are talking about. There are many other versions of the population balance equation, but you can refer to some other excellent review papers that specifically discuss on the different types of population balance equation. But here, what we are looking at are the continuous and deterministic type of population balance equation. So the general population balance equation that we have here is shown here, right? This is what we have looked at the past video. So there are a few terms, a few primary terms in the population balance equation. So the first term here tells us how the number density evolves with time. So you have the partial derivative of the number density with respect to time. The second term here tells us how the number density evolves with the internal coordinate space. So as we mentioned in the previous video, let's say if you have a system, again we use a particulate system where your particle is capable of growing or shrinking with time, then you would have this so-called velocity through the internal coordinate space, and then you would involve this term in order to model that growth or shrinkage of your particle through the internal coordinate space. So this is represented by the second term in the general population balance equation. And this x dot here is the velocity of your particle, or in other words, the growth rate or the shrinkage rate of your particle with respect to the internal coordinate space. So the third term here is the term that tells us how the number density evolved with the physical space. So here you expect that if you have a fluid that is moving, then your particle will be moving with the velocity of the fluid. Then you'd have, this is the velocity of the fluid, and then you'd have the particle moving throughout the physical space. So this term actually accounts for that. So if you wanted to model your system, and it is important enough for you to track the movement of the particle throughout the physical space, then this is a term that you would deal with in the population balance formulation. All right, but if your number density of your particle, you consider them to not be dependent on the spatial coordinate, then you can drop this term and just model the entire system as a system that is purely dependent on the internal coordinate space. Okay, so it's essentially it's just a well-mixed system that you're trying to model. And the first term on the right hand side here is the birth or the death term, or usually we say that this might be the sink or the source term, where you actually account for additional physics like the aggregation of the particles. So two particles joining together to form one larger particle, or you can have one parent particle breaking into smaller particles. So the aggregation and the breakage term is being accounted for in this term, the first term on the right hand side here, which is your sink and the source term. So this is the general population balance equation that we spoke about in our previous video. But in our video series here, we are more interested, or rather I'm more interested in actually going into each term, and let's study them in detail to understand the population balance equation better, so that we can apply them more appropriately, right? Instead of treating them just as an equation, we want to learn everything that we need to about the population balance equation so that we can actually use them more efficiently and use them, more importantly, to use them correctly to model our process of interest. So in this video, we are going to look at how a 1D population balance equation can emerge just by considering the concept of a number balance. So remember that in our previous video, we spoke about that the number density is the thing that we wanted to model by using the population balance modeling approach. So here we have the number density function, right? This is the thing that we are actually after. And the number density function, we have also introduced the fact that it is in general, if we actually write them in general, it is a function of the internal coordinate, which can be your crystal size, the age of a cell, or the degree of polymerization of your polymeric system, right? So it's a general function of the internal coordinate as well as the external coordinate, which is your physical space, okay? And it can also be a function. I mean, very obvious, we wanted to model it. We wanted to model how the number density actually changed with time, so it has to be a function of time. Okay, so this is the number density function that we are after for our process. Whatever process that you are dealing with, this is the term that you are going to want to be focusing, right? You wanted to model the evolution of the number density throughout the internal and external coordinate space and with time. So the number density function here, it tells us the number of particles per unit volume of the physical space, okay, and per unit volume of the internal coordinate space. So we say per unit volume of the internal coordinate space here, but in general, the internal coordinate space can be multiple dimensions. It can be more than 3 dimensions, 4 dimensions, 5 dimensions. But in general, if we consider this as a volume, the entire domain throughout all the internal coordinate space, we consider this as the volume. In the physical domain, it's easy for us to imagine because we always have 3 dimensions in our physical space, and we straight away we know that by our physical intuition that the volume of the physical space is a 3-dimensional volume, right? But in the internal coordinate space, you can have more than 3 dimensions. So whatever it is, the entire space is what we call the volume. Okay, so in trying to understand how to construct a population balance equation by considering the balance of the number of particles, we need to be able to speak of the concept of particle fluxes, right? It's just like what we have done for transport phenomena when we build the continuity equation. We actually talk about the mass flux, right? We say that the mass density, the rho mass density multiplied by the velocity of a fluid, for example, the mass density multiplied by the fluid velocity will give us the mass flux, right? And then in the Navier-Stokes equation, we talk about the momentum flux, and in the energy equation, we talk about heat flux and so on. So in order to construct a population balance equation, which we say is based on the idea of the balances in the number of particles, right? We need to be able to consider the idea of particle fluxes. So in this case, because our number density is a function of the internal coordinate as well as the external coordinate, we need to be able to consider that the number of particles, the fluxes of the particle, can be through the internal coordinate space, which means that your particles can be growing or shrinking, right? It changes in size for that same particle, right? That specific particle over time, it can grow or it can shrink. So we need to consider the particle fluxes over the internal coordinate space. And at the same time, if we are considering that the particle can move with time through the physical space, then we need to also consider the particle fluxes through the external coordinate space or our physical space. So these are the two fluxes that we need to consider. So analogous to the concept that mass flux is just the mass density multiplied by the velocity of the fluid, here the particle flux is just the velocity through that particular space that we are talking about. For example, if we are talking about the flux of the particle through the internal coordinate space, the flux will be just the particle velocity through the internal coordinate space multiplied by the number density function. So x dot multiplied by n will give us the particle flux through the internal coordinate space. And then the flux of the particle through the external coordinate space is just simply the velocity of the particle, right? You can most of the time we assume that the velocity of the particle takes on the velocity of the fluid because it's the fluid that is eventually pushing the particle. So you can say that it's the velocity of the particle through the external coordinate space multiplied by the number density function will give you the flux through the physical space. So these two fluxes are the main terms or the main thing that we need in order to build the population balance equation. For a generic population balance equation, we will generally need to consider the fluxes through the internal and external coordinate space. So I will leave it to you here to verify that the units of these two entities, whether it's the velocity through the internal or external coordinate space, multiplied by the number density function, which is given here that it is the number of particles per unit volume of physical space, per unit volume of internal coordinate space. I will leave it to you to verify that the multiplication of these two terms here indeed gives you the fluxes of the particle through each domain. Okay, so let's just first try to further make sense of the particle fluxes. So let us consider now that we have a Cartesian coordinate system here, which is being represented by three directions, right? In your physical space, you have three directions, and you can say that these are represented by three unit vectors in each direction, and we call it, let's say, E1, E2, and E3. So let's say that now you want to look at how the particle fluxes, you want to look at what are the particle fluxes through the external coordinate space or the physical space. So in this case here, we are going to say that this r dot here is the velocity of your particle through the external coordinate space. And most of the time, this will be equal to the fluid velocity, right? Because as we mentioned, the fluid is the force that is moving the particle around. So let's just say that the velocity, okay, is represented by a vector component r dot 1 E1 plus r dot 2 E2 plus r dot 3 E3. So this is your velocity of the particle through the external coordinate space. So if you take this velocity, right, in this coordinate system and you actually multiply it with your number density function, then this is what you are going to get, right? You multiply the velocity vector through the external coordinate space with the number density function, you are going to get three components. So this will be the flux through the number one direction, right? This is the component of the flux through the external coordinate space in the one direction, physical space. This will be the flux in the physical space through in the two direction, and this will be the flux through the physical space in the three direction. So you can see that this multiplication of the velocity vector with the number density function actually produces the flux, the total fluxes, and you can decompose them into multiple directions depending on the coordinate system that you are using. So similarly here, the flux through the internal coordinate space can be imagined to be of the same nature also, dependent on how many dimensions that you have in your internal coordinate space. So now we are ready to look at a simple number balance concept, the concept of number balance using the population balance modeling. So let's just look at it now. So let's just first consider a system that is sort of more simplified, right? Let's consider that firstly, we neglect all the special dependence, which means that your number density function now, let us just first assume that it is not going to be a function of the physical space. Okay, so this is a very well-known generalization in chemical engineering, where we always say that when a system is well mixed, then it has no spatial dependence. So let's just say that the number density, right, we can write it as just a function of the internal coordinate and time. Okay, and then let's just further make one more simplification and say that instead of having multiple dimensions in the internal coordinate space, let us just say that we only characterize our particle with only one internal coordinate. For example, if you have polymerization, let's just say that the only thing that is characterizing the internal coordinate would be the degree of polymerization. So you only choose a 1D internal coordinate in order to characterize the system. So let's just say that now we can write our number density function as just a function of a single x and time. Okay, let's just make this simplification before we go on to illustrate the concept of how the number balance really is and how it can give you the population balance equation. So because of the simplifications that we make, then we also say that the velocity or the growth rate, if you have a particle growing, or if you have the opposite where the particle is shrinking, then you have the shrinkage rate. Okay, so we say that the velocity through the internal coordinate space is only a function of x and t only. Okay, so with this assumption here, let's just take a small slice out of the internal coordinate space and just analyze the number flux balance, right? So let's just now look at this space here, whereby in the internal coordinate space x, between 2 points A and B here, let's just say you have 2 points A and B, and we wanted to actually analyze the flux that goes into this domain here defined by A and B, between A and B, and the flux that goes out between A and B, and whatever that is whatever that is being produced or being consumed within the region here, right? We wanted to do a number flux balance essentially over this very small domain here between A and B in the internal coordinate system. So in this case here, can we say that the flux that is going in to this domain here, can we say that this is simply the velocity or the growth rate or the velocity of the particle through the internal coordinate space multiplied by the number density? We can, right? Evaluated at x equals to a, right? This is the flux that is going into this domain here. Okay, so we can write the flux in as such. And in the same way also, the flux that goes out of the system, we can also write it as the velocity in the internal coordinate space multiplied by the number density evaluated at this point B, right? Because we are evaluating the flux that is going in and going out over these two boundaries here. Okay, so this is the in and the out. This is the flux that goes in and out of the system. But what about the particles that you generate or consume within the domain itself, right? So that would be the birth or the death, or in other words, we call it the sink and the source term here. So this would be represented by an integration of the source and the sink term over the domain between A and B, right? Because when you can have some big particles breaking into small particles that fall into this region, that creates the birth, right? And you can have particles from this region here breaking further and falling out of the region. So this will be the death term, right? You are losing particle from the region, but at the same time, when larger particle breaks into this region, you can have particles that that is being born in this region here. On the other hand, if you have aggregation, you can also have two smaller particles that aggregate together that forms a particle that falls into this region between A and B, or you can have some particles within this region A and B that aggregates together and it will fall out of the region between A and B. Okay, so whether it's aggregation or whether it's breakage, there will be particles that is being born in the system and the particles that is being discarded through the system because of these birth and death processes, and this will be represented by just the integration over the entire domain from A to B of this source or sink term. Okay, so with this term here now, we will be ready next to proceed to write the number balance. So now finally, after establishing all this in the previous slides, now we are ready to start writing our number flux balance. So as with any material balances, so we would need to be able to write the balances as accumulation is equals to in minus out plus whatever source and sink, right? So this is the typical balances that we write for all our physical systems. So how do we write the accumulation term here? So the accumulation term here is just simply d dt of the integration over this domain from point A to point B of your number density function, right? You integrate the number density function over dx from A to B, and because of this integration now, the number density is only a function of time after the integration. So it becomes from a partial derivative becomes a ordinary derivative. So this is the accumulation term that we can write. And the in and out is what we have written previously. It will simply just be the velocity multiplied by the number density evaluated at x equals to a. The out, the flux going out of the system, okay, would be the velocity through the internal coordinate multiplied by the number density function evaluated at x equals to b, plus the source and the sink term, which is what we have discussed at length just now, where we say that the source and the sink term, the number that is being born or being discarded through these 2 points here in the domain is simply just the integration from a to b over the source or the sink term. So this is how we write the number flux balance. So after we write this material balance or the number flux balance here, can we further simplify this equation? It turns out, of course, we can. Because if we look at the first term here, which is your accumulation term, we can use the Leibniz rule to rewrite this as this, right? You can move the derivative in using the Leibniz rule, and then you'll be able to write the accumulation term as such. And for these 2 terms here, I can write this first, right? I can write the out first, and then I can write the in, right? As the I simply just rearrange the terms and I leave the source and the sink term as such. Okay, so can we now further write these 2 terms here in the form of an integral over the domain from a to b? It turns out that we can. We can write this as integration from a to b of this derivative over the internal coordinate of your x dot multiplied by your number density function. So the slides are here, right? You can refer to this and you can work it out on your own to make sure that you can actually, from this point here, you can actually get this point. Show for yourself that you can actually write this as from the second line to the third line. You show for yourself that you can actually do this. So now that we have managed to write every term here as an integral between a to b, then we can rearrange this easily, right? We can just put everything together, put all these terms on the left hand side and rearrange them within the integral, right? So we can show that integration from a to b of this whole chunk here is going to be equals to 0, right? This is just simply a rearrangement of the equation. Now, from this point here, because of the assumption that our internal coordinate and all the variable needs to be smooth, right? It needs to be smooth and continuous over the integrand, and this will lead to us being able to conclude that this expression here can also be written as equals to 0 because of the fact that the integration, everything within the integration must be sufficiently smooth over the domain from a to b. So then we can write that whatever is in the integration is equals to 0, right? So rearrange it, we will be able to get this equation, which is a 1D population balance equation that has no special dependence, right? This is the simplest form of the population balance equation that we can derive by simply considering the concept of a number flux balance. So again, just to quickly recap, this would be how the number density evolves with time. This will be how the number density evolves with the internal coordinate space, right? This is the velocity through the internal coordinate space, which can be your growth rate or your shrinkage rate. And this right hand side here, similarly, is going to be your birth or your death term, which we say that this could be the breakage term or the aggregation term. So in the simplest case, if you're trying to model a 1D case whereby you say that your system or the systems of interest can be modeled by considering a one-dimensional internal coordinate, then you can use this equation here to model your physical systems of interest. So that is all for this particular video. I hope you enjoyed this video, and my main intention of this particular video is to illustrate to you how the population balance equation in a very simple 1D form can evolve and can emerge as a number flux balance. And so if you find this video helpful to help you in understanding the population balance equation, please feel free to leave a like, subscribe, and leave a comment down below to tell me what kind of video you want me to produce in the future. If you have any question, please feel free to drop it down at the comment section below, and I will be happy to discuss with you on anything about population balance. So I'll see you in the next video.